Okay, in this section, we're going to see yet another new method for solving first-order differential equations that may or may not be linear and may or may not be separable. So before we get to this method, and also before we get to a description of what an exact differential equation is, we need to bring up a useful result, which is the equality of mixed partial derivatives. So this is a fact from multivariable calculus that is going to be relevant to the way we solve these equations. So let's consider the function fxy is equal to, say, x cubed sine of xy. Okay, so we've been taking partial derivatives, and we're going to take partial derivatives again today, but we're going to see an interesting property of them. So let's start by taking the derivative with respect to x. So the partial of f with respect to x, we can see, well, that would require the product rule. So the derivative of x cubed is 3x squared times sine of xy plus x cubed times the derivative of sine of xy. Well, that would be cosine of xy. And then that's multiplied using the chain rule by the derivative of xy with respect to x, which would just be y. So let's tidy this up a little bit. Okay, very good. So what we're now going to do is take the partial of this partial derivative with respect to y. So think of it like the partial with respect to y of the partial of f with respect to x. And this can be written as, and what it is it's the partial derivative of this expression with respect to y now. So it's not going to be as bad as it looks, because remember, when we're taking a partial derivative, everything except for, in this case, y, is going to be considered a constant. So 3x squared times the sine of xy, well, that 3x squared is just a constant, so this is going to be 3x squared times the cosine of xy, and we'll multiply by the derivative of xy with respect to y, which would of course just be x. Plus, here we will need the product rule, so the derivative of x cubed y with respect to y, that's just x cubed, and multiplied by cosine of xy, plus x cubed y times the derivative of cosine of xy, which would be negative sine of xy, and then times the derivative of xy with respect to y, which would be x. Okay, so cleaning this up, you can see we have 3x cubed plus another x cubed, and those are the coefficients of xy. So we'd actually have 4x cubed cosine of xy minus x to the fourth times y sine of xy. Okay, so there's our second partial of f. This is called a mixed partial because we took one derivative with respect to x and another derivative with respect to y. In fact, we have a more convenient notation for this kind of thing. The partial of f with respect to x can be simply denoted with f subscript x. So this guy here would be denoted f subscript x followed by y. So we took the partial with respect to x and then the partial with respect to y. Okay, so now let's go back to the beginning and let's take the partial derivative of f with respect to y. So x cubed is a constant, so that's x cubed. Derivative of sine is cosine of xy multiplied by the derivative of y, which is x. So we get x to the fourth cosine of xy. And again, we can call this f subscript y if we wanted. Now we're going to take the partial derivative of that with respect to x, which is the other mixed partial. So, okay, we need the product rule here. Derivative of x to the 4 is 4x cubed multiplied by cosine of xy plus x to the fourth times the derivative of cosine of xy, which would be negative sine of xy, times the derivative of xy with respect to x, which would be y. So what we get is 4x cubed cosine of xy minus x to the fourth y sine of xy. So that's our second partial of f with respect to y followed by x. And we could write this using this notation. Derivative f with respect to y followed by x. Okay, so why are we having this lesson on multivariable calculus? Well, because there's a wonderful result, it's often referred to as Clairaut's theorem, that says that the mixed partials will be equal to each other under good behavior conditions. So that's the case here. Notice that fxy is equal to fyx. And this is a fact that we actually need in order to work out this particular category of differential equations. All right, well, how does this apply to solving differential equations? Well, let's suppose that we want to take the derivative with respect to x of the product x times y. Well, we know by the product rule that this is the derivative of x, which is 1 times y, plus x times the derivative of y with respect to x. Okay, and if we multiply both sides by the differential dx, then we get the differential of xy is equal to y dx plus x dy. Now suppose we didn't know that the right-hand side were the differential of x times y. And all we knew is that we had a differential equation written in differential form that looked like this. Well, recall that this term here we referred to as m, and this term here we referred to as n. Well, there's a simple test we can apply to m and n to see whether or not this expression here is the differential of a multivariable function. If we apply this simple test and it's successful, then we'd be able to construct the fxy using a simple integration process. By integrating this differential form, we'd get fxy, and integrating the 0 would give us a constant. So we would simply have an expression involving x and y equals c, and we'd be done. Or you could isolate y if you wanted in that solution. So what is the test? Well, the test is merely to see if the partial of m with respect to y is equal to the partial of n with respect to x. Because that's like comparing the two mixed partials. And if they are equal to each other, then yes, that means that this differential equation must be the differential of some function. And we can construct that function using integration. In that case, we would consider this differential equation to be exact. If the answer is no, meaning the partial of m with respect to y is not equal to the partial of n with respect to x, then sadly this is not exact, and, well, we have to try something else to solve this differential equation. Okay, so in order to solve the differential equations in this section, we're going to write them in differential form. We're going to check to see if they're exact, and if they are, then we're going to integrate either m or n to find that multivariable f function, which will equal the antiderivative of 0, which is a constant. And then we'll be done. So let's look at some examples. All right, so the technique is kind of complicated to write down, but easy to demonstrate and easy to carry out. So this is one of those situations where we're going to look at how to do it by example, sort of like learning integration by parts, which is easier just to show by example. So the first thing we need to do is check to see if this differential equation is exact. All right, so here we have our m, and here we have our n, and the differential equation is exact if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. And you can't just swap the x and the y rule there. The idea here is that m is already the first partial of this mysterious f that we want, this potential function. M is already the first partial of that with respect to x. So by taking the partial with respect to y, we are building the mixed partial derivative, and n is already the first partial of f with respect to y. So by taking one more derivative of n with respect to x, we get the mixed partial. And if these mixed partials equal each other, that means that the function f actually exists. And we can go find it. So we need to check if my is equal to nx, and we'll do that by evaluating both of them. So partial of m with respect to y, okay, that's equal to 2x. Partial of n with respect to x is also equal to 2x. So we can see that my is equal to nx, and therefore the differential equation is exact. Okay, if it turns out that the differential equation were not exact by this process, then you would just abort this altogether and go back to the beginning and try a different technique. This particular differential equation is linear in y, and it's also separable. So we actually have many methods that we could use to solve this one, but we're going to solve it this way because this is what we're learning right now. Okay, so once we have that the differential equation is exact, what we're going to do is we're going to construct our f by integration. F of xy can be constructed either by integrating m with respect to x, or by integrating n with respect to y. Think of it like you've got your differential equation in differential form, and you have your choice of either integrating this thing or integrating that thing. So you just pick the one that's easier. Now both of those look pretty straightforward, so I think let's just go with integrating m dx. Okay, so m is 2xy. Again, y is just regarded as a constant for this integration. So this is going to be x squared times y. Now, normally we'd say, oh, plus a constant here, right? Except that constant right there may involve the letter y. I mean, let's suppose that instead of a constant, we had like cosine of y squared or something. And then we took the partial derivative of this whole thing with respect to x, we would still get 2xy, right? We'd get 2xy out of that plus 0, because the derivative of cosine of whatever that is with respect to x would be 0. Okay, so how do we represent a constant when it could have a y in it? Well, we just call that g of y for now. Okay, now we're close to being done, but not quite, because we do need to determine what g of y is. So how do we determine g of y? Well, we're going to take the derivative of this thing with respect to y, and that's supposed to give us n. Okay, so the partial derivative of x squared y with respect to y is x squared, and the derivative of g of y is g prime of y, and that's equal to what n was, and n was x squared plus 4. So we conclude that g prime of y is equal to 4, because the x squareds cancel. Ah, okay. So we can deduce that g of y is equal to 4 times y. Ah, what about the constant? Well, we're going to leave it off, and I'll explain why in just a moment. But where does that put us right now? Well, we finally have our fxy, which is x squared y plus g of y, and g of y is 4y. So now we're going to set fxy equal to a constant, which is the antiderivative of 0. And remember, 0 is on the right-hand side of the original differential equation. So that's our final answer. Well, x squared y plus 4y equals c. That's our final answer. And you can see why we didn't include the constant back at the g of y step, because we could have just added that constant over to the other side and had a new constant. Okay, let's verify that this really works. So if we have x squared y plus 4y equals c, okay, let's take the derivative implicitly here. We want to find dy dx. So we need the product rule here. Derivative of x squared is 2x multiplied by y plus x squared times the derivative of y plus 4 times the derivative of y equals 0. Multiply everything by dx, and you get 2xy dx plus x squared plus 4 dy equals 0. And there it is. There's our differential equation, actually emerging naturally from the implicit differentiation. So we win. All right, with this one, we notice that it's not linear or separable. So we need to test for exactness and hope that it's exact, because if it's not exact, then, well, we don't know how to solve it. So let's first check for exactness. Okay, well, this stuff here, there's our m, and all of that stuff there, that's our n. So we're going to check if my is equal to nx. Derivative of m with respect to y is equal to the derivative of n with respect to x. Okay, there's a lot of little detail here, so make sure that you practice enough of these so that you're not stumped on the detail. So the derivative of m with respect to y, which means we're treating x as a constant here. So all we have to do is bring that 2 down, so we get 6x squared y minus a constant times y, so just that constant, which is 3 over x, and the derivative of 6 is 0. So there's our my, and let's see if that's equal to nx. Derivative with respect to x of 2x cubed y minus 3 ln x is equal to 6x squared y minus 3 over x. Ah, very good. So indeed, my is equal to nx. So the differential equation is exact. Hooray! What this means is that the mixed partials of some particular unknown f are equal to each other. So that unknown f actually exists. And we're going to find it by integrating either m with respect to x or n with respect to y. And this time I say we go n with respect to y. It's only got 2 terms. The other one's got 3. Ah, okay. Well, antiderivative of this term here with respect to y is actually just x cubed times y squared. And the antiderivative of this term with respect to y is simply 3y ln x. Remember, ln x is a constant relative to y. So we just needed to multiply that term by y, which is what we did. But there is this residual term here, which we're going to call h of x. So it could involve stuff with x in it. It's a constant relative to y, but it, of course, might have x. So to figure that out, we're now going to take the derivative of this whole thing and compare it with m. Okay, so the derivative with respect to x of x cubed y squared minus 3y ln x plus h of x is equal to 3x squared y squared minus 3y over x plus h prime of x. And the original m was 3x squared y squared minus 3y over x plus 6. Aha! Well, that tells us that h prime of x is equal to 6. And therefore, h of x is 6x. And again, we're going to just not worry about the constant because we know we can just push it into that final constant at the end. So we can conclude, well, f of xy equals c is an implicit solution to this differential equation. Well, what's f of xy? Well, that's x cubed y squared minus 3y ln x plus h of x, which is 6x, and that's equal to a constant. Final answer. All right, look at this little one here. So, well, let's start by writing it in differential form. It's not quite there yet. We need to get everything on one side with 0 on the other side. In other words, that's this plus this equals 0. So let's move that thing over. Minus. All right, excellent. So this big old thing is our m, and this big thing here is our n. And actually note that n includes the minus. Let's actually distribute that negative so that we don't have to worry about it anymore. There we go. All right, let's check and see if this thing's exact. So we're going to take the partial of m with respect to y. Okay, so this is 2 times y times some stuff. So that's just going to be 2 times the stuff. So 2 sine x cosine x. But you know what? Let's write that as sine of 2x because of that old identity. Derivative of y with respect to y, that would be 1. And it looks like here we're going to need the product rule. So derivative of 2y squared, that's 4y times this exponential plus 2y squared times the derivative of the exponential. So e to the stuff again, but multiplied by the derivative of the stuff with respect to y, so that would be 2xy. Okay, let's clean this up. Spectacular. Okay, now let's find the partial of n with respect to x, and let's hope that it equals that thing, or hope that it doesn't, because if it doesn't, then we get to just stop, right? Okay, so this is a derivative with respect to x. So we have negative 1 plus derivative of sine squared. That would be 2 sine x and then cosine x by the chain rule. Hey, that's the sine 2x guy right there. And we'll use the product rule on this thing. So derivative of 4xy with respect to x, that would just be 4y. And then 4xy times the derivative of e to the xy squared. That'd be e to the xy squared times the derivative of xy squared with respect to x, which would be y squared. So we get, after cleaning it up, Okay, comparing nx with my, looks like they're identical. Hooray! Okay, so to find f, we're going to either integrate m with respect to x or n with respect to y. So let's go see which one we want to do. Neither one looks particularly delicious, so I say we just go with m with respect to x. See what happens. Okay, so this is one heck of an integral. What we certainly could put right here is y times, again, sine of 2x, makes that a little bit nicer, minus y plus 2y squared e to the xy squared dx. And yeah, let's integrate. So we know the antiderivative of sine is negative cosine. And with this 2 coefficient, we can do a quick u substitution, which brings out a factor of 1/2. So we're going to get negative y over 2 cosine of 2x. Again, we are integrating with respect to x, so this is simply going to be y times x. These y's here are constant, so it's going to be like 2y squared times the antiderivative of e to the xy squared. But in fact, let's just work that out now. That's going to be e to the xy squared divided by y squared. Okay, if you can't quite see what happened right at the end there, we just used this fact here that e to the bx dx integrates to e to the bx divided by b. So again, we're just treating y as a constant. So this cleans up a little bit. We get negative y over 2 cosine of 2x minus y times x plus 2 e to the xy squared. And oh, you know what we forgot? That g of y. There we are, g of y. Okay, so now we're going to take the derivative of that with respect to y and compare it with the original n. Okay, so the derivative with respect to y of this thing, well, that's equal to negative 1/2 cosine of 2x minus x plus 2 e to the xy squared times the derivative of xy squared, which would be 2xy, plus g prime of y. So cleaning that up, we have negative 1/2 cosine of 2x minus x plus 4xy e to the xy squared plus g prime of y. And the original n was negative x plus sine squared x plus 4xy e to the xy squared. Okay, so it looks like these terms coincide, these terms coincide. What about this sine squared and the cosine of 2x? Well, you may recall from Calc 2 that sine squared of an angle is 1/2 1 minus cosine of twice that angle. Or it could be written as 1/2 minus 1/2 cosine of 2x, which means that n is actually negative x plus 1/2 minus 1/2 cosine of 2x plus 4xy e to the xy. Very good. We can now see that g prime of y is equal to 1/2. Okay, and therefore g of y is 1/2 y. So now we can put together our final answer. We know that it's going to be this f of xy that we found, setting it equal to a constant. And I'm going to call the constant c1, and you'll see why in a moment. So fxy is, of course, negative y over 2 cosine of 2x minus y times x. Oh, let's write that as xy, alphabetical, plus 2 e to the xy squared, plus g of y, which we now know to be 1/2 y, and that's equal to that constant, c1. All right, very good. So now this would be perfectly acceptable as a final answer, but wouldn't it be nicer if we just cleared out the fractions? There's no need to have them. We could multiply everything by 2, and in fact, we can multiply everything by -2, and we'd get y cosine 2x plus 2xy minus 4 e to the xy squared minus y is equal to our final constant, which is -2 times that first constant. And there we are. Ah, okay, an initial value problem. So that, of course, means do everything you need to solve the differential equation, and you're going to get a one-parameter family of solutions. But when you're done, plug in 1 and 1 for t and y and solve for the constant, and then you've got your particular solution, and you're on your way. So that sounds like lots of fun. First thing we should do is write this in differential form. And we'll multiply everything by dt. So we get t over 2y to the 4th dt plus all of this stuff dy equals 0. And notice the order of the terms I put here with the independent variable differential first and the dependent variable differential second, so that we don't mix up our m and our n. So there's m, there's n. Okay, well, we should probably check to see if this thing's exact. And we're going to do that by taking the partial of m with respect to y. Okay, so that's like the partial derivative of t over 2 times y to the -4. All right, well, that would be -2t times y to the -5, so that's -2t over y to the 5. Okay, let's check n sub t, the partial with respect to t of all that stuff that was n, which is this, 3y squared minus t squared over y to the 5. And you might look at that and think, oh, great, quotient rule. But no, remember, y is just a constant. So we can write this as the derivative with respect to t of 3 over y cubed minus t squared over y to the 5th. And the derivative with respect to t of 3 over y cubed is just 0. So this is like 1 over y to the 5th times the derivative with respect to t of t squared. So this is -2t over y to the 5th. Ah, very good. It equals that thing. These are the same. So yes, the differential equation is exact. Okay, well, now we know it's exact. That means that some potential function f of xy exists, and we're going to construct it. So we'll either integrate m with respect to t or n with respect to y. Let's go see which will be easier to work with. Oftentimes it really doesn't make a difference, but you might have one integral that's much harder than the other, or even impossible. So probably be a good idea to avoid an impossible one. looks like it'd be pretty easy to integrate m with respect to t, so let's do that. Okay, and again, remember this is just with respect to t. Y is a constant, so we can, I know it seems weird, but you can just pull it right out of that integral like that. So what we get is t squared divided by 4y to the 4 plus our constant relative to t, which would be a function of y. All right, next, to determine g of y, we're going to take the derivative of our f. Whoops, I just noticed something. This isn't f of xy. This is f of ty. We should probably use the right letter. Okay. Yeah, when I was a kid, I skipped the episode of Sesame Street that was sponsored by the letter T. Okay, so to find g of y, we're now going to take the partial derivative of our f with respect to y, and that should be equal to n. All right, so the partial of, let's write this as t squared over 4 times y to the negative 4 plus g of y. That's equal to, the negative 4 comes down and we get negative t squared times y to the negative 5 plus g prime of y. So that's negative t squared over y to the 5 plus g prime of y. And our n was equal to 3y squared minus t squared all over y to the 5. So in fact, we could write that guy as 3 over y cubed minus t squared over y to the 5. Aha! We can now see that g prime of y must be 3 over y cubed. We'll write it like that because we know we're about to integrate that thing. So our g of y will be 3 over negative 2 times y to the negative 2, or negative 3 over 2y squared. So the general solution, which is f of xy equaling some constant, let's call it c1 because we know there's fractions involved, is going to be what we got for f. So we've pasted in the f here. That's equal to the constant. G of y we know is negative 3 over 2y squared. So we have t squared over 4y to the 4th minus 3 over 2y squared. That's equal to our constant. Okay, and we can multiply by 4y to the 4 to make the expression, to make the solution a little cleaner. So that would give us t squared minus 6y squared equals c times y to the 4th, where c is equal to 4 times c1. But remember, this was an initial value problem, so we actually can determine the c by plugging in the given point. Y of 1 was equal to 1. So t is equal to 1 and y is equal to 1. So we have 1 squared minus 6 times 1 squared is equal to c times 1 to the 4th power. Okay, so c is negative 5. And so our particular solution is t squared minus 6y squared is equal to negative 5 y to the 4th.